Problem 6.2. There are two questions that are more like, in a sense, theoretical or not numerical like the other problems that we usually do, right? So the first one is, let f be a function defined on the closed interval 0, 1 and mapping values on 0, 1. And if f is continuous and surjective, okay, that means that every value in this interval has the mapping values from this cover the interval 0, 1. Okay, in particular that means that it covers 0 and 1 and every value in between, right? So prove that there exists a c, okay, in this interval such that f of c is equal to c, right? Okay, so suppose what's this function like, right? So this is 0, 1, right? 0, 1. And a function like this, that's defined like this, that's surjective, right? It's something like this. It starts like this and then goes like, it doesn't matter what it does, right? But at some point it touches 1, right? And then it can come down, and in this case it has to come down all the way to 0, right? Because it hasn't touched. Okay, so it has to touch both 1 and 0, right? So there are many ways to approach this problem, but the idea here is that we have this function, right? If you define this function g of x, right, is f of x minus x, right? And we have g is continuous, right, because it's a combination of two continuous functions. Now g is defined also in the same interval 0, 1 and 0, 1. 0, 1, but it maps values from -1 to 1 in principle. Asking that there is a c such that f of c is equal to c is asking that there is, or proving that there is an x, or let's say there is a c in this interval such that g of c is 0. Okay, that g has a root in this interval 0, 1. Okay, so now if you see this, right, we need to prove that a continuous function has a root in an interval, in a closed interval. Then that calls to mind using Bolzano's theorem. Okay. Okay, so how do we use Bolzano's theorem here? Okay, so there are two possible cases, extreme cases, right? Suppose if we have the function at f, right, at 0, this is 1, 1, right? If the function is 0 at 0, right? Okay, it should be going like this. Sorry. If the function is 0 at 0, if f of 0 is 0, then we're done, right? Our c is 0. The first case, right? Now, for the second case, we have that our f of 0 has to be greater than 0, right? So our function starts something like this, right? And so now we have that two possible outcomes, right? Either, let's call it A. F of 1 is 1, right? And then we're done, then C is 1. Okay? Because then we have a function like this. Or, yeah, sorry. Can't do it like that. It has to go to 0, and then at 1 it's equal to 1, right? If that's the case, then our C is C. But then we have the third possibility is that f of 0 is greater than 0, and then f of 1 is smaller than 1, right? So what happens then, right? So let me rewrite this clear. F of 0 is 0, f of 1 is 1. What happens if both f of 0 is greater than 0 and f of 1 is smaller than 1, right? Well, then we have this. Let's see. If f of 0 is greater than 0, right, then we have that g of 0 is greater than 0, because we have something that's greater than 0 minus 0 is greater than 0. But g of 1 will be something that's smaller than 1 minus 1, so this is smaller than 0, right? So in other words, these things imply that g of 0 is greater than 0, g of 1 is smaller than 0. So that means that there is a, because g is a continuous function, there is a c, in this interval that fulfills g of c equals 0, right? Using Bolzano's theorem. So that means that g is a function that does something like this. It starts here, right? This is -1, this is 1, and this is x1. So g will start something here, right? Because f of 0 is greater than 0. And then it will decrease until it gets to here, right? And at some point, somewhere in the interval, it crosses the axis. Okay? I hope that's clear. B says, suppose we have a function f that is continuous in this closed interval a, b. And again, whenever we have continuous functions in a closed interval, we can think of applying Bolzano's theorem, the intermediate values theorem, things like that, right? And let x1, x2, xn, so there are n points here, distributed along this interval a, b. Prove that there exists a c, okay, in this interval, such that the value of the function at c is equal to this sum, okay, this is the average of the value of the function at these endpoints, right? You sum the values of the function, okay? We have, this is a, this is b, and suppose we have, for instance, I don't know, this function, right? And this is x1, x2, x3, x4. So here n is 4, right? So then we have, this is f of x1, f of x2, f of x3, and f of x4, right? And I don't know, if you compute the average of that, right? This is going to be somewhere in between these guys, right? So it's going to be something like this, right? Maybe, I don't know, or something like this, okay? This is the average. So there's a value here, c, such that f of c is exactly this average, right? And so you get the idea, because the average is going to be between the highest and the lowest term, and the function is continuous, it's going to take every value in between. So there's going to be a c that has this particular value, okay? That's the kind of the graphical idea. How do we prove this more rigorously? Well, we have this value, right? We have 1 over n, sum of k equals 1 to the n of f at these points, okay? These endpoints. Now, this is an average, this is a value, okay? Let's call it mu from, it doesn't matter, right? It's just a number. Now, f of x f of xk from k equals 1 to n, it's going to be like n different values, right? So there's going to be a maximum for them, right? The maximum of f at x1, f at x2, blah blah blah, f of xn, right? And it's also going to be a minimum, because this is a finite set. So in finite sets, there's always a minimum and a maximum whenever you have real numbers, right? So the maximum and the minimum. Right now, so m is going to be greater or equal than each of these ones, right? So it's going to be, if we sum m n times, right, this sum is going to be greater than this sum, because m is greater than each of these terms in this, greater or equal than each of these terms in this sum. And the same thing if we sum from k equals 1 to the n, m, right, small m, and divide by 1 over n. M is going to be smaller than each of these terms in the sum, right? So now this thing is bound in this sum from below, this thing is bound in this sum from above. So we have, if we sum n times m, we have n times m divided by n is m, smaller or equal than 1 over n times the sum from k equals 1 to the n of f at this points xk. And again, if you sum m times n times m, you have m times n divided by m, sorry, by n, it's m, okay? So we have that our value is between this m and this capital M, right? But we know that our function, okay, there is a value, let's call it x sub m, right? Such that f at x sub m is small m, and there's another value x sub capital M such that f of x sub m capital M is capital M, right? So in a sense, the image of f in this interval between x sub small m and x sub great M is going to be between m and m and capital M, right? So the image is going to be between this and this, right? And because of the intermediate value theorem, we know that every point in this interval is going to be visited by f, okay, in this interval, okay? So let me state it more precisely. So in this interval xm, or the other way around, if x capital M is greater, right? The image of f is going to be the close interval from small m to capital M, or at least contain it, right? But we're supposing there are no more no numbers for which m and n for which the value of the function is greater than this, but let's going to say it's going to contain it, okay? So this is going to be a subset of this image. Now f is a continuous function. Because of the intermediate value theorem, it's going to cover every value in this interval, right? Now this value is between these two numbers, so it's in this interval. So there's a point C in this interval a, b, such that f of c is this number, okay? The 1 over n, the sum from k equals 1 to m of f of x at k, right? This is because of the intermediate values theorem.